Bila je možda veća struktura od vodovanja.
Imali smo 3 domaće zadaće, to je bilo
To su bile kao za sjeli.
Pa malo veće ništa.
Da, jesi ti sviđa slučaj?
Bodor.
Da.
Morali bi pogledati, pa ne znam što sam ne znam što ne vidim.
Možemo to ne javiti.
Od nastavne aktivnosti od prošlog trimestra?
Pa ne, ja sam od prošlog semestra.
Da, znam. Mailom će biti teže.
Mislim da ti se to tu i vidi. Ali to ćemo raditi staro predmetu.
Da, znam.
Da to ostane ili da je malo lakše.
Da, takvim udjel ostavimo kako su bile prošle semestre.
3 domaće zadaće su bile, mislim, 5 bodova, onda je bio još onaj labosa, valjda. I prisutnost je bila, tako je bilo 2 bodova.
Kužem. Koliko je sada? 4:11, dobro. Evo sad ću ti izvrši uopće. Sad kao ja, jedno, tako 15 sekundi kasnije, u odnosu na real time, ja ga sad pomaknem, sad znači dole na nulu. Sad je ovdje na nuli. To mi je test, znači da li radi. Sada nam stižem reprodukciju, da mi ne radi feedback, ne. I znači, normalno bi još i Teams bio aktivan uz to, tako da ti koji su udaljeno spojeni, ne, onda mogu kroz Teams...
Ti si niko javio da će ti se...
Nije, danas ti se ni ne javio, ne, ali de facto ovo ću im poslati, znači da te snimke postoje, ne, tako da mogu offline kao gledati.
Ajde pogledaj, da vidiš od prošle godine.
Od prošle godine, sad ćemo se gledati.
Od toga ne vidiš. Da znaju da ćemo.
Sad baš ćemo vidjeti da su makli, danas smo makli, da, to sam već vidio, ali kod nastavne aktivnosti ste mogli da vidjeti. I onda sad tu kažemo,
Misliš da su prikopirali od prošle godine?
Ne, to ne znam. To ne znam, ali možemo vidjeti kada je bilo prošle godine. Sad tu kažemo 2019. ljetna. Sad vlada kao konsolidna nastava. Predavanje na labosu, domaća zadaća. Bodove su nemeka. Bodove. I sad se tu nešto kao vidi, ne? Labos je 15, domaća zadaća 15.
Tako je, i 5 za prisutnost.
I 5 za prisutnost. I onda se osobi nešto znanja.
Ispit i završni ispit.
Da tako ostane?
Da, prema
okej.
Užiša svi dio.
Sad ćemo da vidimo kaj je. Da vidimo samo kaj piše na ovim službenim stranicama od ovog predmeta. Da budem sad otvorio i se sam normalno.
To vjerujem.
Odbrano. Sustave. Sad imate neko bodovanje. Pa se vidi struktura, ne tako.
Ništa nismo unijeli, tako da
Da. 15. Na ovo prisutnost
3
5.
put 5, 3 put 5 i 5.
To ne oče. Tu ne piše, da? Dobro. Okay. So hello. Now it's time, yes. So I greet everybody at the first lecture. Just a second. Okay, so the name of the course is Multimedia Systems. And besides having Croatian students, we also have 3 students from abroad, from Erasmus exchange. One is from Poland, one is from Italy, and one is from Turkey. Maybe if you could introduce yourself and just to know who is who. So what's your name?
I'm Hubert.
Okay.
From Poland, from city Szczecin. But I'm actually studying at city Poznań. And
so you are staying only this semester, this
yes,
summer semester here?
I think only for 1 semester. And at my university I'm on the 6th semester.
And the colleague is from?
I'm from Turkey. I'm from school.
Okay.
Actually, I'm graduated from electrical engineering, and now I'm continuing with electronics and communication engineering. I studied at Istanbul Technical University for 4 years, and now I'm here.
And the last colleague is from Italy?
Yeah, I'm Agostino. I'm from Italy. I study at Projector Milano, and this is my 5th year, the last year of my master degree.
Okay.
I will be here only for a semester, and I study telecommunication engineering in Italy, and here I'm
Okay, I understand. We have, besides 3 foreign students, we also have 5 or 6, I guess, Croatian students. And it would be nice that during the break time you should introduce each other, such that you get the contacts from the colleagues, and they can help you with different assignments or whatever for the course, in translating the materials, maybe, or in helping understanding the announcements on the website and everything else. So that would be the best way that you have direct communication with Croatian students. I hope they are fluent in English as well, and they will be able to help you with the course. Nevertheless, since the lectures will be given in Croatian, then for that reason we have the course book for this course, and this course book, I will show the information about the course. It is also available here. So this is the description of the course, and at the end of this description we have this list of course books that are very useful for this one, for the multimedia systems. So 3 books are shown here, 4 books: Fundamentals of Multimedia, Image and Video Compression for Multimedia, Data Compression, Introduction to Data Compression, and Multimedia Systems. Out of these 4, which one is the best suited for our?
Fundamentals of Multimedia.
The? Fundamentals of Multimedia. Okay, this one is probably the best suited for this kind of course. Okay, we will share this information with our students, and it is a large book, and we will suggest several chapters from the book that cover exactly the topics that we will be given in Croatian, that more or less follow exactly the same structure of the course and everything else. And we will try to have the same time organization for these chapters from the book with the organization of the same material in the course materials that will be given in lectures. In this way, you will be able to follow all the topics that are covered in the course. And we will also have some kind of exam for you that will be, let's say, adjusted to the sections, to chapters that we have covered from the book. So usually after the end of this chapter, we have technical questions and problems. We will select maybe some questions from this list, and you will be given these questions for your exam. So now I will try to switch to Croatian, so that also our Croatian students get the information about the course. But nevertheless, still in English, this is Professor Sonja Grgić. And Professor Sonja Grgić will be giving the second third of the course. The course will be divided in 3 thirds. So the first third will be given by me. I will explain later a bit about the organization topics in these 3 parts. The second part, that is more related to video signals, to video processing, will be given by Professor Sonja Grgić. And the last part is given by our colleague Daniel Hoffman. We are all coming from 3 different departments. So my department is Department of Electronic System Information Processing, and Professor Grgić's department is who knows what?
Who knows?
Wireless technology and space technology.
Space.
Wireless and space technologies, okay? And the last department that colleague Hoffman comes from is automatics and computer engineering. So control and computer engineering. Why so? Because each of us has expertise in each particular part of these topics, of this course, and that is the reason that we have this kind of organization that several professors from different departments are giving part of the course individually. Okay, and for each of the parts of the course, for each of the thirds, we will have also teaching assistants that will be engaged in helping you in organizing the laboratory exercises and exams, midterm exam and final exam. And for the first part, the colleague name is Branimir Dropulic. Branimir Dropulic will be teaching assistant for the first part of the course. For the second is Josip Vukovic, yes. And for the last one, I'm not sure, but he will announce. Daniel will announce who will be a teaching assistant for the last part of the course.
He will be teaching assistant.
Okay, so that is more or less the main things I wanted to say to you. And we have this information package, this ECTS information package. You enrolled to these courses based on the information that you found in this information package. So you have some basic information about the course here. You have English and Croatian version of the same document. And this course, originally last year, it was called differently Multimedia Technologies. Now, this year, it's changed name to Multimedia Systems. It will not be changed dramatically in the content. Maybe the last part will be changed a bit, but more or less the first and second, third will be similar to the course Multimedia Technologies. And for that reason, currently we have 2 websites. One website for the new course, Multimedia Systems, and the former website for the Multimedia Technologies. But they will be, we will use the alias. So we will take the old website and map it to the new course. Okay, and so all the information from the previous course, from the last year course, will be now available on the new course, Multimedia Systems. And I will open this website just to show you how this website is organized. Okay, so if I go to the main page of the institution, okay, so, sorry, intranet, not now, intranet. So if you after you log with your credentials, on the left side, you will have all the courses that you are enrolled to. And one of these courses is Multimedia Systems, multimedijski sustavi. And this is this new website, but we will use the original website, so not Mulsus, Multech. So this is the original website from the former course, from the last year course, Multimedia Technologies. This will be mapped to the new course. So it will be just exchanged. And we will edit all the information from this that is not relevant anymore from the previous website and update it to the current version for the multimedia systems. Okay. The information is more or less in Croatian, but nevertheless, Google Translate works very good. So if you just Ctrl-C, Ctrl-V, you will get the translation that is quite close to the ideal translation. I am quite astonished with the quality of this automatic translation nowadays. It was not that good a few years ago, but nowadays it works quite well. And so the materials, for example, I have opened the sub-page lectures, predavanja, and on this sub-page we have the presentation that will be shown for each of the lectures. And for example, if I click here, MT02, it will be for the second week of the course. It is here, so if I open it here, okay, coding of media signals. For all of these chapters that are covered by the course, we have the corresponding chapters in the book. And we will be giving exactly page from this to page that. You have to cover it by yourself. We'll have consultation time for you if you have any question. This consultation can be in person or using any online technology, Teams or whatever. The other thing is also we will create a Teams group for the course. So Microsoft Teams is a tool that is available for our institution because we are paying subscription at the government level. And we will create a multimedia systems special Teams group. All students will be members of this group. And you can also use this Teams group to communicate each other or to lecturers or to teaching assistants to have any information about the course. It will be also used, this Teams group, for online laboratory exercises. If we organize them as online, depending on the current epidemiological situation. So we are not at this moment certain what will happen with corona and this stuff. So if it stays this way, we can have also laboratory exercises in person. But if anything goes up with the numbers of infections and everything else, then we will have to skip to online laboratory and online lectures. And for that reason, this camera here is recording me, and this recording goes directly to YouTube, and YouTube is currently streaming the same video from this room. And if I share the link for this YouTube channel, you can see the live pictures as we are talking now, with a delay of approximately 5 to 10 seconds, depending on the current situation with the traffic. And since this YouTube is one-way communication, and then we use this Teams channel as a return channel if we want to ask questions. So we have YouTube in one way, only streaming, and in parallel we start the Teams meeting, and you can ask questions using this Teams communication. So that will be in the case that we have to switch to online. But as far as we can now use the in-person lectures and in-person laboratories, we will try to use them as much as we can. Okay, so I can just ask our Croatian colleagues, how much have they understand of all of this? So koliko se uopće razumjelo od ovoga kaj sam vam sve ispričao za naše strane studente? Sve. Ajde, ko ima problema sa engleskim da mi kaže, ne, slobodno kažite, ne, jer ako bilo ko ima problema, ja ću ipak onda na hrvatskom ne dominantno pričati, jer znači ja jesam jedne godine, već i više godina, na predmetima gdje sam imao strane studente, koristio hrvatske materijale, ali sam govorio engleski. I na taj način je studentima koji su bili Erasmusni bilo lakše pratiti ta predavanja, pa makar su imali kasnije snimku englesku, a materijale su mogli prevesti već, ne, tako ne, offline sa nekim Google Translateom. Da li vama bilo problem da se, znači, ta predavanja ja pričam na engleskom, ne, a da onda recimo oni razumiju kaj ja pričam, a jasno, materijali su svi na hrvatskom i ispit bi bio na hrvatskom, ništa ne bi bilo drugo na engleskom, osim samo predavanja. Koliko bi nam to radilo probleme? A? To bi moglo biti. Dobro, znači možda je to rješenje, kažem, to sam ja uspješno radio par godina na nekim drugim predmetima i nije bilo problema, studenti su svi bili zadovoljni. Na taj način izbjegavamo potrebu da 2 puta držimo predavanje. Znači onda držimo 1 puta predavanje na engleskom. Za vas, hrvatske studente, svi ispiti, svi materijali su daje na hrvatskom. Samo bi sama predavanja onda bila engleska kako bi studenti mogli profitirati koji su došli iz drugih država. Može onda? Ok.
Jedino što za njih moraš onda provjeru znanja prilagoditi, njih moraš i s njime, ne?
Da. So we have just discussed with our Croatian students whether they would mind to have the lectures in English in a way that you can all follow in English. For them, the exam will be in Croatian, and they have also the materials for the course in Croatian. But if I give the lectures in English, although maybe slides are given in Croatian, you will be able to understand because you will have the recording available in English, and you could also translate these few sentences from Croatian to English. Okay. You will see later on that most of these slides, they do not contain much of the text. So it is usually some mathematical expressions, maybe some images, figures, and so on. So there isn't that many textual slides. And if there are, I will translate them in English. I will tell the whole thing in English so you will be able to understand. Okay? Now, question from your side, maybe some part of the scoring. So how your final mark, final grade for the course will be. Okay. So for Croatian students, we have these percentages, znači za kontinuirano savladavanje, percentages for this continuous assessments. And last year, the last semester, we had the same situation with Corona, with COVID, exactly the same time as now, and we had to stick to the online teaching. And for that reason, we have changed a bit these percentages, how much you gain based on the homeworks, how much you gain based on laboratory exercises, and finally for the presence on the lectures. We have also some small percentage for the presence at the lectures. And these percentages will increase a bit, such that you will have less stress on passing the midterm exam and the final exam, in a way that now you get 50% of points from these homework assignments. You get from each part of the course, from first third, second third, last third, you get 1 homework, and you will get 5 points for each of these homeworks that you complete. So this altogether 15 points. Then the same thing is for the laboratory exercises. They are also organized in 3 parts, and you also get 5 points for each of these 3 laboratory exercises for the first part, second part, and the last part. And finally, we have these 5 points that is based on your presence at the lectures. So if you are present for all 13 weeks that we have these lectures, you get these 5 points. Otherwise, it is linearly scaled based on how many times you have attained the lectures. Okay, and then we have this midterm exam and final exam. They are 1/2. And we have this oral exam. It is only 10 points, I guess. 10 points. Okay. Now, questions from your side? Did we cover more or less everything? If yes, then now we have introduced ourselves. If you have any questions, you can ask questions either by mail or later on by Teams once we initialize this Teams channel. Okay? Sonja, can you still share? That's my next question. Yeah. Okay, then for this introductory part we are done, and we can start with the actual content of the course. Okay? Sonja, hvala. Ok. Odmah. Okay, now I will open this first lecture for the first presentation. Okay, MT01. Okay, so this is like an introductory lecture about multimedia technologies, about multimedia systems. So what is multimedia? Što je multimedia? It has many meanings. The basic definition would be it is media that combines several connected or interconnected types of content in order to better present some information. So you have some information, you would like to present this information in the best possible way. So you take different modalities, different media types in order to present this information in a way that is easier understandable. The opposite of this multimedia is classical content sources, like books, like newspapers, and everything else, where we have only textual information, maybe some images, some figures, maybe some tables. Then, sorry, I have to use this. The basic idea is how to use this multimedia to extend this kind of primitive or dull content with additional media. And this additional media can be audio, signal, some narration. It can be mono signal, stereo signal, or even multi-channel audio signal. It can be, let's say, music, but also pure speech. So speech signal, narration. Then we can also have video content, and in some cases, animations. For some application, it is very interesting to use stereoscopy. These sources that have two individual video channels recorded, they simulate the view that you have with two eyes. As one channel for the left eye, the second channel for the right eye, and based on presentation of these two channels independently to each of the eyes, you get the depth information. So this kind of stereoscopy is available nowadays, and the most typical way that you have this stereoscopy in everyday use are these virtual reality systems, where you have a really independent image from the left eye, from the right eye. You have these goggles, and these goggles project different images to each of the eyes. And since these images are digitally generated, they trick your brain in creating the depth information. So somehow you are seeing the third dimension because the angle for this image from the left side, from the right side is different. And based on this different angle, we have this stereoscopic image. And it is used in this virtual reality environment. By combining this multimedia content, we get much more attractive content that is adjusted to the user, to the viewer. And regarding the focus of our course, so if you have these multimedia systems, this multimedia system as such would be constructed based on these lower levels. And these lower levels are more or less main topics of this course. And this would be manipulation with the content, so how to store, transmit, analyze, or search this information, how to synchronize information, but that is the highest level. And the lowest level starts from the media itself. So we have input or output media. And after that we have recording or reproduction based on the direction. So either we record this media, that would be in this direction, from the media to the system, or the other way, if we use this system for reproduction, then the output signal is transmitted to the environment as some kind of media signal. Then we have this step, and that is digitalization or representation of this media signal in digital domain. But this raw representation, let's say high rate representation, is usually not suitable for storage or for transmission, because this media signal, they usually have very high rates, high data rates. And for that reason, I would like to add this block in between, and what it does is some kind of coding or decoding. In this direction, it is decoding. So some compressed signal is decoded and sent to the DA converter, and finally reproduced as a media signal. In this direction, it is encoded. So the raw signal after digitalization comes at the entrance of this block, and this block performs coding. And this coding is, the main reason for this coding is to reduce the rate, and while still retaining the full information about the signal. I don't want to lose anything. I want to keep all the information that are relevant for reconstruction, and I want to remove only the redundancies. If there are some redundancies in the signal, I want to remove them and model these redundancies by the model. Okay, finally, once we have this signal that is encoded, we can manipulate these signals, either by storing it or by transmitting it over the network or by analyzing. Nowadays, it is very popular or very common to see the application of artificial intelligence algorithms that are capable of analyzing still images or even video images and extracting content from these images. For example, you might make a query, find me all images that have a red car on the image, or find me all images that have yellow submarine. And so it will simply, based on this kind of semantical question, search all the images that really have this object contained in them. It can be also video sequence. Try to annotate in which video sequence some movie actor is present in the stream. So I don't know whichever. So tell me at which minute, at what time instant in the stream we get the full frame with some actor. So that would be analysis or searching the multimedia content. Okay, and finally, this is the core of the multimedia system. But we also have this online web content. We have online services and users. And finally, we have multimedia application. All these three parts are communicating with this core part that does this digitalization, coding, representation, and some basic operations on the digital media. Okay, our course will have the significant emphasis on this part here. Not on the online web content, not on the application, but on this low-level signal representation, signal coding, and manipulation. So we will consider the realizations, or so how this lower level of multimedia systems are implemented on computers, but not only on computers, but nowadays on any of these embedded platforms, like your mobile phone. So all of this is performed using the CPU that is part of your mobile phone. It is not a single CPU. It is typically multi-core CPU that is present in each of your telephones, mobile phones. But beside this multi-core CPU, it is typically some kind of ARM architecture, 32-bit, whatever. Beside this 4 or 8-core ARM RISC CPU, you have also typically 3 dedicated signal processors, digital signal processors, that are based on their architecture customized to do exactly these operations on media signals, either on audio, speech, on video stream, so video coding, decoding. What do I mean customized? Their architecture is suitable or suited to energy efficient processing of such signals. All of this can be done on the main CPU. All of this application can simply be compiled and run on the main ARM CPU, but in less energy efficient way. Because to do the same operation, you have to make more switching, more transistors have to change state, and then you have larger energy consumption. So you have lower efficiency, and of course you drain your battery on a mobile phone if you do it a lot. If you do it for a long time, then you quickly drain your battery. And that is the reason why they have a dedicated digital signal processors beside this ARM architecture that are only adjusted to energy efficient execution of these digital signal processing tasks that are characteristic for multimedia systems. Okay. So these are these low-level multimedia operations. Okay. In the first part of the course, we will cover introduction to multimedia technology and systems, architecture and applications. We'll cover the medias. What kind of medias do we have? What kind of medias do we represent or transmit? Then some basics about coding and compression. We will show how this idea can be applied for the speech signal. So how can I efficiently model and analyze the speech signal and get the parametric representation that is suitable for encoding. This here was the basics of the digital communications, digital mobile phones. So previous to these GSM phones in Europe, they had only analog phones. So the information, speech information was transmitted as analog signal. But with the advent of this speech signal modeling in time discrete domain, we were able to take the speech signal from the microphone, to analyze it, to convert it to parametric representation. Then simply encode these parameters. These real numbers are converted to some integer numbers, and these integer numbers are finally transmitted over the communication channel. So it is more or less this mobile phone as having a computer that is capable of digitizing the input speech, running an algorithm that performs analysis, modeling, and this parametric representation, quantization of these parameters, and simply transmitting these parameters over digital channel. That is what is done in a mobile phone. And at the beginning, it was limited to very primitive, let's say, coding quality. This first standard, GSM standard, was not that good, I would say. The quality of speech was comparable to the analog telephone line of that time, but it was of much lower quality than we have nowadays with the current mobile phones, with the current coding standards. And one reason why it was inferior to the current coding standards was also the rate. The data rate that was used in the first GSM standard was relatively low only 13 kilobits were available as a data channel transmission rate between your mobile phone and the base station. So this mobile base station and your mobile phone were connected with a two-direction communication with 13 kilobits per second in each of the directions. It was not that much, and the coding quality was limited by this data rate. Nowadays, you know that you can have several hundred megabits of communication speed between your mobile phone and your base station, and for that reason, it is not any problem anymore. So you can encode live video and stream live video over this digital channel because the data rate is sufficiently high to convey this information. Okay, so this is about speech signal coding, because more or less this speech signal coding started the whole transition to mobile phones, to digital mobile phones. We will say something about standards for speech coding and some basics about synthesis and speech recognition. Usually we don't have time to cover this last topic, and that would be audio signal and psychoacoustic model for the audio signal, and that is the one that is used in all of these audio coders, like MPEG, this MP3, it is typically called. So this audio encoding standard takes into account the way that humans are able to understand sound, to hear sound. We can hear, we have the perception for certain parts of the spectrum, for certain parts of the time domain waveform, but some things we cannot hear. And if this representation error or quantization error is exactly in these time parts or spectral parts that we cannot hear, then we simply we cannot understand, we cannot resolve whether this is original signal or quantized signal. They really, to us, they are the same. We don't have any difference between the quantized and original signal, because the idea is that these coders use this psychoacoustic model. They know exactly what you can hear and what you can't. And if the quantization error is put into this region that you can hear, no problem. It sounds perfect. Okay. The topics for the second and the last third I will skip right now, and Professor Grgic and later on Professor Hoffman will cover these topics in the second and the last third. Okay, so this is more or less like a historic coverage of the topic of multimedia signals. I will show now how the application of multimedia looked like in 2008. So these slides were first prepared in 2008. So it is 13 years from today, okay, in the past. So let's see how this, for example, online information media use the multimedia to enhance their content. For example, here is one of our daily newspapers, Jutarnji List, Jutarnji HR. So it was their website of Jutarnji from 2008. Definitely, you can see it was slightly different visual experience, slightly different technology. It definitely evolved in 13 years in between. It was the same thing for another daily newspaper, Večernji List. This is from our national broadcaster, TV broadcaster, Croatian radio and television news. And more or less, their website is the same as it looked 30 years ago. It didn't change that much. So it was in 2008. And then, for example, here you have MTV website, and then some application now in communication. In communications, we have, as I said, mainly in digital mobile phones. It says here video telephony, third generation UMTS. Nowadays we have this fifth generation 5G networks. what is the difference, main difference? So it started from this first generation. We had only 13 kilobits data rate between your mobile phone and base station. That was it. The raw data rate was 19 kilobits, 19.6, but this difference between 13 and 19.6 was used for channel coding, so to enhance the resilience to network errors. So if you have random bit errors, you have to correct these errors, otherwise you cannot decode the stream. And if you have this, first generation GSM of total 19.6 kilobits, this difference between 13 and 19.6, so 6.6 kilobits, were used for this redundancy coding. So how to protect the information that you are sending, because the network will introduce random bit errors at the reception side. So you can either identify that the block has an error and try to retransmit this block, the whole block. So you send the information from the receiver to the transmitter. Please, I have not received the block correctly. Could you retransmit the block once more? Or the other way, if you use these error correction codes, you can really use this redundancy information to correct the wrong bit. So you exactly can pinpoint which of the bits was wrong and correct the proper value for this bit. In this way, you are able to get, let's say, after correction, several orders of magnitude lower bit error than it was in the actual transmission. Maybe in the actual transmission, 1 in 1,000 bits were totaled, but after application of this correction, it is 1 in million or 1 in 10 million based on this redundancy. How much bits you add to the information to create this redundancy, it determines this resilience. So after decoding, after channel decoding, what would be your final bit error rate? Okay. We will not be covering the aspect of channel coding that much in this course. It is covered more or less maybe in a larger extent in a course named Information Theory. So we have this Information Theory course. In this course, this aspect of channel coding is covered in more detail. Okay. Then nowadays we have this 5th generation mobile networks, and what do they differ from the first generation? Exactly in the radio part. So the radio part is different. Transceiver, receiver, transmitter. It uses different parts of spectrum, much wider bandwidths of the spectrum are used for communication, and much higher carrier frequencies. So for this 5th generation, exactly for this very high rate communication, if I want to achieve several hundred megabits per second data channel between your mobile phone and network, you would be using carriers that are in very high gigahertz range, 20 gigahertz, so on. And these channels are very wide, because in order to be able to have the rate several hundred megabits, then this channel must be several megahertz wide, several megahertz wide. And that is the reason that they push this carrier frequency to this unused radio frequency spectrum, very high gigahertz range. And that is what is now used in this 5th generation mobile networks. Some parts of the spectrum that were not used previously for other application. Why? Because they did not have technology, output amplifier, antennas, and so on, to transmit and receive signals at such high frequencies. Nowadays, they really have advanced these electronic components, and they can have reliable radio communication at very high carrier frequencies. One of the drawbacks of this using very high frequencies is that the propagation of such signal requires optical visibility between the antenna of the transmitter and antenna of the receiver of your mobile phone. If you don't have the optical part in between, this signal is not propagated. It is attenuated. It cannot go around the corners. If you have some wall in between, concrete wall or whatever, the signal cannot pass through this concrete wall. It must be really free direction for the propagation of this high frequency signal. And that is the reason that the antennas and for 5G network, antennas for the base station must be much more densely organized in the space than with previous generations of networks. With 3G, 4G, we could have one mobile base station for each several hundred meters, even several kilometers apart. But with 5G, these base stations are much smaller. Local cells are much smaller, maybe only a few hundred meters large, because you must have this optical visibility between the antennas. Okay. Now it's 2 minutes past 5. Now we can make a break, 15 minutes break. If you have any questions, you can ask after the break or during the break, as you prefer. Okay? Just a few service information. So I will open this automatic door at the end of the corridor, but to exit the corridor, there is one button on the left side of the door. You cannot open the door unless you press this button. So you first press this button, then take the handle and push the door. Otherwise, you cannot open the door. And I will activate this automatic entry that you will be able to return if you go outside the corridor. But I have to update it once in 1 hour. Okay. We have also some balcony here, so for those that are smokers can use this open area for smoke break. Okay. Then možete raditi Okay. Schaden. Yeah, higher, further out, forward. Okay, questions? Any questions regarding the last presentation? So now we'll speak a little bit about the applications of multimedia, not only in communications, but in the interactive presentations, multimedia content. Of course, every one of you knows about the PowerPoint, that you can use PowerPoint to make attractive presentation. Previously, it was Adobe Flash. Nowadays, this Flash is completely dead, so it is a product that is not supported anymore. And but more or less, it was a very interesting idea, also in the sense that early websites had a problem with the connection speed. And if you wanted to have some kind of animation, attractive animation, they were limited by the connection speed between the server and your client. And this Adobe created this Flash standard that was able to circumvent this limit, connection speed limit, and create really interesting or attractive animations, more or less animations, with in parametric representation. They were compressed quite a lot. Okay, and but it was proprietary standard, and it was not implemented in the browsers at that time, in Microsoft browsers or whatever, and more or less it became obsolete. And one of the reasons was also the instability of the implementation of the platform was not written properly, and it caused crashes and other problems. So nowadays it is really completely eliminated. It is not supported anymore. Then we have this Movie Maker, Adobe Premiere. So that were tools to make movie content, to do the editing for the movie content. Early communication systems that were IP-based. So in 2008, telecoms still use their proprietary telecommunication channels, dedicated channels. But later on, in the last 12 or 13 years, practically all of these telecom providers have migrated to IP, to Internet Protocol. So all data flow is done through the Internet network. All the content, so speech, audio, whatever, TV channels like Netflix or whatever. So everything is transmitted to the conventional IP Ethernet channels. At the beginning, so you had these dedicated communication channels between the infrastructure and between several communication providers, but you had to pay for this usage of the network. So for your voice call, you had to pay, I don't know how much at that time, for each of your voice calls. And to circumvent the cost of this paid service, the idea is that if you have a company that is have several offices around the world, you would use exactly IP connection to connect these several companies in between. And inside one of these sites, you would have conventional telephones that will be connected to this corporate network. And in this way, you could go around the classical communication channel, use the IP communication channel, avoid the cost, and still use the standard terminals, standard telephones in your offices. Today, it is also completely obsolete concept, more or less, because nowadays, even in offices, practically nobody uses a fixed phone. You don't have a fixed phone, more or less everybody has a mobile phone. Wherever you work, in any kind of financial services or whatever, each of these employees have mobile phones, and they use it for everyday use, but also for the professional use. So today, it is migrated completely to mobile networks. But for example, how this first video teleconferencing application looked like, this is application running on a PC using some webcam. Of course, you have it nowadays in any sort of platform implemented, and some early mobile phones that were multimedia enhanced or supported were able to establish video communication. This one was only for playback, but for example, in some cases you could have a camera and have a really voice call between two telephones. And it was like state of the art at that time in 2008. It was not a normally available phone. And in 2008, you had the iPhone of the first generation, 2007 to be exactly. This first generation iPhone was released to the market in 2007. But even that one did not have capability to do the video coding and coding in real time and to transmit this video sequence in both directions to have a video call between two telephones. It could be used only for capturing still images. So it had camera, but this camera was not capable to record a movie at all, only still images, the first generation iPhone. Only the second generation, they have enhanced the software support in the way that the same camera could be used for capturing the motion video, the video. Okay, then this is how YouTube looked like in 2008. And at that time, the rate was the limiting factor. Not the rate of the infrastructure, but the rate that the typical user would be connected. So broadband connectivity was not available at that time. You would be happy with 2 megabits ADSL or something like that. And all of this content has to be tailored to fit into such low bitrate channels, several megabits, 1, 2, 3 megabits, or even less than that. Then application in multimedia in education and science. Different, of course, in universities and scientific content are usually enhanced with multimedia content. If I, for example, I'm trying to open this, it doesn't work, but I will open the normal maps. If you, of course, all of you are familiar with using, okay. With Google Maps. Okay, so we are here, Faculty of Electrical Engineering and Computing. We can zoom in, zoom out into this digital map. And finally, we can activate the satellite image. If I activate the satellite image, I get the same view as it is seen from above, from the satellite. But what is also very interesting with this Google Maps, you can have this street view as well. So if I take this little man and put it somewhere, for example here, I will try to see how it looks like from the human perspective. So here is the building, this deep building we are right now in, and you have just been here on this balcony from the deep building, okay? So this image was taken with a specially equipped car. So this car had a mast on the roof, and this mast had several cameras that were simultaneously capturing 8 directions. So more or less you had a coverage 45 degrees in each of these 8 directions. And there is also one camera that was oriented to the sky. And that is the reason I can turn this virtual view even up to exactly 90 degrees above me. Because there was one camera that was capturing this part of the space. But what you see here is that you cannot really find where these images are connected. Maybe here, you can see here that I have this kind of strange behavior. Why? Because one image is from the left side and the second image is here connected, and this connection is not ideal. This stitching is not done ideally. And how all this is performed? It was, if you open here and if I say Street View, Wikipedia. How this was done? It was a project that Google started just to record each and every possible road on the surface of the Earth. So to go around with this kind of car, so you see the car, and on the rooftop you have this mast, and this mast has this camera system with several cameras oriented in 8 directions. One camera looking to the sky, and these cameras are normal still cameras, but what it also has, it has GPS, such that it knows exactly where this car was located when the image was taken. So the location of the car was known. And what it also has, it has this LiDAR, and LiDAR is this laser radar. Laser radar it emits laser pulse in all directions, so it rotates around and it elevates in angle. It emits this laser beam and measures the reflection. And based on the reflection, you have this time of arrival difference. It measures the distance between the car, between the LiDAR, and the wall and the building. And through this image, through this measurement, you can get the 3D space. So you can really measure how far you are from the wall, the building, how this building is tall, because you have all this information measured by this time of arrival of laser reflected beam. Okay. This is called LiDAR. This here is a coverage in what year, I don't know. Blue is very highly covered. Africa is not covered, you can see here. But North and South America are covered. China is not covered, or not covered that much. You can see here how this thing is implemented. These two are these LiDARs, this one and this one. And this here, this ball are these cameras. Each camera covers 45 degrees. Okay. Next. If you have this part of the city where car cannot enter, pedestrian zone, in this case they would use this kind of tricycle. So for the tricycle, again, you have this mast system with the cameras, and they can go into the pedestrian zone to also take images in this part of the town. It can be also carried with a human. So a human can take this backpack and go around to take these images, measurements in some areas where a car cannot enter. Another implementation. And going around those different cities in the world, you could see this kind of car. It has this Google Street View logotype. And these are some historic previous versions of this system. Okay? Human operated version. And they also had for the ski slopes on this ski mobile truck, they had this system also mounted, and they would go around all the ski slopes in Italy or Austria, and you would have the street view even for the ski slopes. Okay? And it is a huge undertaking to go to each possible corner of the world and take one set of images from here, go 10 meters further, take new set of images, and go on and go on. So there are billions of photos that are taken, and they are stored on some servers. And now, if I want to browse this content, it is done directly from the either Google Earth application or Google Maps. And what is also, it is not maybe visible here, but what do I have to do? There is possibility to have this bird's eye view, but that maps the actual image on 3D models. So exactly using this LiDAR information, they were able to create 3D models of each building in Zagreb. And if you take this view, it is not simply bird's eye view from the top, but you can have the projection from any angle. And in this case, it projects or renders this image on the 3D model. And you get the really accurate visualization of the space. I don't know what I have to do. In Google Earth, it doesn't want to open here. I'm trying, okay. It has some problems either with network or whatever, but otherwise in Google Earth, I will be able to zoom from above. As I go down in the elevation, at some elevation, it changes to this 3D modeling. Okay, exactly this one. Okay, so this, you can see here, this is a 3D model. And this image is rendered on top of this 3D model. I like to use this Google Earth as an ideal example of multimedia application. Why? Because it has enormous quantity of information behind it. So you have millions and millions of images, either taken from the sky with satellites, or taken from the ground level with these cameras. And this system is capable of combining everything together and changing the view to any view I'd like. I simply use some kind of, I don't know how to use this rotation, because this mouse is probably too simple for the interaction. But you can see that all of these buildings are really modeled as 3D models. I can go around, scroll, and they have it practically for all major cities in the world. How it is possible that it is freely available, it's hard to understand. It is only based on advertisement, that Google somehow makes money once you click on some ad. And of course, it's not that the only source or the only motivation. Probably it is also the Department of Defense and security agencies. They are also interested to have this kind of information available. If they want to have some military intervention in Zagreb, then they exactly know where they have to go. Okay, you can go in any of these gardens inside. Okay, there's some building here. Okay, you can go in here. Okay, so this is enormous value for the information security guys, let's say, or military guys, if you have this detailed spatial information for any city in the world. Just going around, you have, okay, this is the garage with the blue door. Okay, something is behind this blue door. Okay, this is a very interesting illustration of multimedia system. It also works with virtual reality goggles. So if you put this virtual reality goggles, you have this special joystick, and with this special joystick, you are able to rotate in all different directions, zoom in, zoom out, everything. And you really get the stereographic view. And it is much more impressive than when you're viewing it with only simple projector, simple screen, one-dimensional screen. it really looks natural. So of these buildings, I can change this height, and if I go deep down, then it will just change to this street view. I don't know what I have to do to change to street view some things. Okay, now I have put a human here, and now I'm in street view. So combining the information from the satellites, combining the information from these kind of moving cars that took these images, they are able to construct this 3D, whatever, 3D model. As you are there, but you are here in Zagreb, and when you are scrolling, I don't know what this is, some foreign city. Okay, so this is a really impressive application, because to be able to do this in real time, to scroll around, and to find the exactly proper image from the database, to stitch these images together, it is extremely high load on the server and on the client as well, to be able to present this information in this way. And a huge amount of human work is done to prepare this material. And also one thing that I want to stress is that all of this is also subject to this personal protection of information. Okay, so if I put, for example, man here, you can see that all the plate numbers are blurred. In Europe, we have this GDPR, that law that protects personal information. And of course, if anyone would be able to read this car plate, then maybe somebody will know, okay, this guy lives here because this is his car, okay, now I can find his flat. For that reason, all of the car plates must be blurred, but also the faces of people must be blurred. You can see here, all of the car plates are blurred. And only this is a huge task. Imagine that you have this million of images in the database. You have to find the car, you have to find the car plate on the car, and blur only this part of the image to avoid to be readable by the humans. If I try to find some people, some persons, the faces should also be blurred. In this way, you should not be able to recognize the person you see here. So this is high resolution image because I can zoom in, zoom out, as you can see. But this part of the image is intentionally blurred to protect the privacy. Okay, I like to show this example because it is really impressive. So to have this automation, to have this result at the end, it took many thousands or whatever millions of man hours to prepare these materials. Okay, now going back. That is this application in Google Street View. Of course, we have application for example, NASA, and nowadays we have this special mission on Mars, new rover that is now has landed on Mars, Perseverance, and it is preparing to go around for several years, as predecessors did successfully. And this rover has altogether 20 cameras. Not only rover, but this part that was used for landing. 22 cameras, I think. So they really understand how important is this multimedia aspect to enhance their presence to as large as possible audience in the world. To have this information publicly available. For example, if I now open NASA Golf, Okay. Perseverance landing video from Mars. No thanks. Okay, play. And this video was recorded during the entry of this rover into the Mars atmosphere. This is deployment of this parachute. So it was one camera that was pointed up, and this is the part that is falling down to the Mars. It is recorded from the upper part of the. Finally, this rover is lowered with some kind of special pulley system to the Mars surface to avoid the effect of these boosters, rocket boosters, on ruining or whatever the rover itself. Because if they are close to the surface, then they create huge blasts of stones and dust. And to avoid this, it is lowered with this kind of pulley systems, with this kind of like ropes. It is lowered down, and they cut these ropes, these cables, and at the end, this upper part that was used to deaccelerate simply flies away, and the rover is on the surface. And this here was recorded with only 3 or 4 of these cameras. But on the rover itself, they have 16 more cameras. Some are for the navigation, some are for scientific exploration, and so on. And all of this multimedia content is now available on these websites of NASA and so on. Vice President Harris calls NASA, okay, nothing, blah, blah, blah. Mars, where's Mars? I don't want to bother. Okay, so this NASA website, how it looked in 2008, you can see they have similar colors, blue color as they did, because this blue color is in their logotype. And they still use this blue color more or less as a dominant color on the website. Then this here was the image from one of the early rovers on Mars that showed stitched panorama. And this panorama was taken, if you can see here that these are individual images. And these individual images were stitched together in this huge panorama. At that time, this camera was fixed focus lens camera. It was not zoom camera. And to create this panorama, this mast was rotated and camera was pointed to different angles in elevation and azimuth. And finally, combined images are used to create this panoramic image. And the rover itself is very distorted because it is also captured with the camera, but it is close to the camera. So that is the reason why it is so distorted. Okay? In 2008, these 2 rovers were 3 years at that time, lively kicking on the Mars, but now they are both dead. Okay. So what we have learned what are the media that we will be exploring in our multimedia systems course. Sorry, I just skipped that one. So the definition of multimedia, definition of multimedia technologies, structure of multimedia systems, and application. These are the topics so far covered by this first presentation. Now we'll skip to the second part, and these are the medias in multimedia. So what are the medias that we will be covering in our course? That is any useful signal that connects human as a user of some information, cognitively interesting or useful information, and a source. So media that we will be exploring are always connected to the human as an observer, either as an observer or as a source. Sometimes human can be source of multimedia information. He can also be the user or source and drain, like a user of information. Okay, the direction of the media stream is important. As we said, human can be source of multimedia or the endpoint for the multimedia signal. Beside the human, sources can also be material world that around us with different sources like natural signals or artificially created signals that can create like a virtual reality presence, virtual reality impression. These signals can be not from the actual world, but virtually created signals, either visual or audio signals that create some kind of virtual space. When we are talking about this latest rover, it was the first rover that landed on Mars that had also the microphone on the rover. And it was capable to record the sound of the wind blowing around the rover on the Mars surface. It is the first time that we have this sound information recorded as well. Signals that we are recording can be divided based on the way that they are perceived. And that is tightly related or directly related to our senses. So what are the main excitation that we can feel? It can be our sight, our hearing, taste, smell, and touch. So these are the 5 senses that we have. So sight, hearing, taste, smell, and touch. Tactile information. And this is like an artistic presentation of these 5 senses. For example, somebody is pouring wine here, so that will be for tasting wine, so it has some taste. Then, I don't know, somebody is smoking a pipe, so that will be for our smell. Then somebody is, I guess, singing or something, playing some music. It is for hearing or for talking and so on. Then, so what is the way that these signals are perceived? They are perceived from receptors. And these receptors for different media sources are mechanoreceptors. These mechanoreceptors are used for the tactile information, for the pressure, for hearing, and for balance. So when we are walking around, this balance is based on mechanoreceptor. When we are hearing also based on mechanoreceptors. Just to be able to understand how it works, let's consider just this case of hearing. So how the human hearing is achieved in our hearing system. So you have this outer ear. So this is our outer ear. No. Sorry. It is connected with a sequence or set of small bones. This outer ear is connected with this set of small bones to the inner ear. And the vibration from this membrane on the outer ear are transmitted over this set of bones to the entrance of the inner ear. So there's a small membrane and the entrance of the inner ear. And this inner ear is looks like a snail, something like that. It is like a tube. It is a spiral tube. And this tube is from the wider radius to the smaller and smaller radius. And once we have this variable air pressure, sound pressure, it creates variations or vibrations of this membrane of your outer ear. These vibrations are transmitted through this set of bones to the entry point to this small membrane of the inner ear. And this inner ear how does it work? So if I unroll this snail-like object, so we have this entrance, and we have like conical shape, and inside this conical shape, there is a fluid. So inside the inner ear, there is a fluid. And this fluid, if I push this membrane left or right, I create waves inside this fluid. And these waves create maximums and minimums. So somewhere around this tube, there will be maximum and minimum, because the waves are reflected at the end and they are superimposed on top of each other. And based on the frequency of the wave, this superposition creates the highest amplitude for given frequency at some point here, x1. For some frequency, f1, I will have the highest amplitude of this mechanical vibration, this motion of this fluid at some place inside the inner ear at position x1. For some frequency, f2, the position that has the highest response would be x2. So I have the frequency to position discrimination, conversion from frequency to position inside this conical tube, where these superimposed waves are added together, and I get the maximum of amplitude. And how to measure this motion of this fluid? This motion of fluid is measured by hearing cells. So here I have groups of hearing cells. Really, they are like small hairs. Like you have hair here, very small hairs that are growing from the base of this tube. And all of these hairs have nerves and nerve endings. And if these hairs are moved left-right, these nerves are excited and they transmit a signal to the brain. So if I have some motion of this fluid around this point, this hearing nerves are excited because these hairs are moving left-right. Like sea anemone, if you have this motion in the sea water, this sea anemone goes left-right, left-right, and this motion of this hearing hairs causes the creation of nerve signals. And this part goes in a bunch to your brain as a block that is related to the frequency f1. Then this bunch goes as a block of nerve signals that is related to signal, for example, x3, whatever. And you have for each of the frequency bands, one block of nerve endings. And in the brain, you get the response. So if I have a repeated signal coming from this block of nerves, I deduce it must be some signal of frequency f1. How many bands do I have along this basilar membrane? It is called basilar membrane. There are 20 bands, 20 blocks of nerves, around 20 blocks. So each of these is dedicated for one part of the spectrum. So I have 20 critical bands. And based on these signals from 20 bands, our brain is capable to understand the pitch of the audio signal, pitch of the sound, whether the sound is higher or lower in pitch. And how we are able to discriminate that many sounds that we are able to discriminate, because if you're playing a piano, you have many octaves in piano scale. So you have start on C, next C, 8, 9 octaves. And all of these frequencies, so you have 12 half tones inside one octave, and then again you have 10 octaves, for example, or 8 octaves. So 12 times 8, you are able to discriminate 100 different tones from very low frequency tones to high frequency tones. And how we are able to understand if it is one or the other tone? Because although we have only 20 bands, several bands are excited simultaneously, and they are overlapping. I will try to show this characteristic curve. So one band, the lowest band is this one. The next band is this one. They are wider and wider as the frequency increases, and their separation is larger and larger as the frequency increases. But consider we have a pure tone, only one signal, only one frequency, F0. This frequency is exciting 3 different bands. This one with this level, this one with this level, and this one with this level. So I get simultaneously three nerve endings response. So from 3 bunches of these nerve endings, I have response signal. But the repetition or the rate of these signals is proportional to the intensity or to the level corresponding to the characteristic of this band, frequency characteristic of this band. So this first band has the highest signal, the second band slightly lower, the last band even lower. And based on the relative relation of these amplitudes, our brain is capable to understand, it is some frequency that is in between this central frequency and this central frequency, somewhere in between. But maybe closer to this one, because maybe the first band was this one. And I had also the response for this first band here. And this one was of a lower amplitude, so I deduce in my brain, the signal is probably closer to this one than to that one. Okay? So it is left from the center of these two. And that is the way that we are able to recognize or to resolve several hundred different frequencies, several hundred or 100, 200 different tones, although we have only 20 bands, critical bands in our inner ear. Okay, so it is a very rudimentary explanation of the hearing system. They have done this measurement on the actual basilar membranes of a cat. So they took out this inner ear from the cat, and they have really excited this inner ear with different mechanical vibration, different frequencies, and they have measured which of these nerve endings produced the significant response based on the frequency. And that is the way they measure this characteristic, frequency characteristic of human inner ear. So it is actually mechanical receptor. Why mechanical? Because you really have the fluid that is moving left, right, and vibrating based on the excitation coming from the outer ear, from the membrane of the outer ear. Just to be able to understand how small vibrations are these here. For the sounds that are the lowest possible amplitude, you are still able to hear. For example, the leaf is falling from this tree and it falls on the floor, and you can hear this very low intensity sound. Okay, the leaf has fallen on the floor. This kind of small signal, very low sound pressure level, produces movement of this membrane that is comparable to the atomic level dimension. So this membrane is moved maybe 1 atom dimension left-right. Only 1 atom dimension left-right due to this excitation of the falling leaf to the floor, to the ground. And this 1 atom you are still able to perceive as some very slight motion of this fluid inside your inner ear, and you get the response over these neural channels. So it is a very fine instrument. So your hearing is extremely fine instrument. And at the same time, you are still able to hear normally sounds or music or speech in loud environments. And that is also very challenging task. For example, you are on some kind of student party. You have 20 students around you, everybody's shouting, everybody's singing something, whatever, and you are trying to understand the colleague next to you, what he is talking to you. And although this environment is really noisy, you have many sources. If you would record this with a microphone, practically this useful information is completely below these different noise sources around you, this different contamination. Still, you are able to resolve your speaker that you are talking to. Why? One reason is that you have these two ears, and you are able to concentrate your hearing to spatial location. You are doing spatial localization. You are like somehow extracting the signals from one part of this space and neglecting other sources that are coming from different angles. So this spatial localization is possible because you have two ears. Otherwise, you would not be able to do this kind of spatial localization. The other thing is that, of course, you use the context. You probably expect what your colleague is telling you, and somehow you are able to extrapolate or to interpolate the words that you haven't heard. You are somehow guessing what he is talking, and based on this guessing, you are still able to understand the whole sentence, although maybe 1/3 of the words were completely garbage in the communication. Okay? So it is really a very challenging task, and if you want to have a computer that does the same thing, it is almost impossible. So to do this kind of processing in a very loud environment where you have many sources, very loud sources, very strong contamination, and to extract only useful information, one person talking to you, it is extremely challenging for automatic processing. For human, we are able to concentrate on one speaker out of this total cacophony of sounds. Okay, now we are at the end of the second. Yes, we are 4 minutes late, okay. 4 minutes past, so we make another short break, but maybe only 5 minutes. Probably we can maybe end 5 minutes earlier, okay? This is the actual image of these hair cells inside the inner ear, how they look like. So like a bunch of hairs, and these hairs have this nerve ending below them. These are this nerve ending, and they, for example, here. So these are these hairs, and in the base are these nerves that are feeling the vibration of the hairs and creating the nerve signals that go along this ganglion, spiral ganglion. Several such intersections of the inner ear. And sometimes when they have this surgical operation for persons that are not capable of hearing sounds for some mechanical reason, then they can create artificial electrical excitation of these nerve endings inside the inner ear. So I have a special device that does this frequency analysis of the source and excites each individual block of this hearing nerves, these hearing cells inside the inner ear to simulate the mechanical excitation, to simulate the behavior of this fluid that is moving inside the inner ear. And these operations are done even for small children, few years old. They are able to have this implant. They make this electrode with 20 different signals along this spiral inner ear, and they excite each of these electrodes excite one region inside the inner ear and stimulate the actual hearing. And they only have to have this outer device that captures the sound from microphone, does this spectral analysis, create excitation for each of these 20 electrodes, and that in this way simulate the actual hearing. And these persons, after this surgical operation, are really able to develop hearing, not immediately. It is not like an on-off switch. You have the operation, you can immediately hear the sounds, understand words or music. It takes some time to learn. So it takes them maybe a few years even to completely learn how to recognize this electrical excitation that is mimicking the mechanical excitation of the inner ear. Okay, we have the receptors for temperature, these thermoreceptors. They are used for our sense of coldness or hotness. So if we are hot, if we are cold, these thermoreceptors are the one that we use to compute or to measure the temperature of the outer space. We have these nociceptors. These nociceptors, they are for the reception of pain. So they are like pain receptors. Each of these receptors, they have a special way how they look. So for example, these are endings in our nose that are used for smell, for sense of smell. These are ends on our tongue that are used for taste. For hearing, this is this base of this hair that moves in this flow of fluid. And at the end of here, I have these nerve endings that go to the brain. And to the left, these are these cells that are used for vision. And one set of cells, rod and cone. One are used for illumination information, so only whether it is light or dark. And the other is used for recognizing color, so whether it is blue, red, and so on. Detailed description of this visual system of humans will be given in the second half of the course. Professor Sonja Grgić will be describing in detail how this human perception of vision works and how it can be used to create systems that are useful in coding and representing video, still images, or live images. Okay. These receptors are of electromagnetic type, so they convert the electromagnetic wave into nerve signals. So if I have a photon of a given frequency falling on this cone, I will have the excitation stronger or less strong depending on the frequency of this photon, because these cones are for the recognizing the color. Okay? And finally, for the taste, for the smell, but not only for taste and smell, but also for oxygen level, glucose level, or CO2 level. We have the receptors in our body that are able to measure the concentration of O2, so the oxygen, of the glucose level. So if we're hungry, so then we have to eat something. We have the receptors for the CO2. And these receptors are chemical receptors. They are in our feedback loop that directly drives our heart. And then we have for the taste and for the smell, again, chemical receptors. These are like a small chemical factories. They have like different reagents, and they test the outside molecules based on reaction with these reagents. And if there is a reaction, then we have smelled something or taste something, like a small chemical factory. It is nowadays one of the challenges to have this sensor for the smell or taste, like additional input device for your mobile phone of the future. If you want to transmit to the other side the taste of your excellent pizza, you take one pizza, whatever part of your pizza, put it on some sensor, and your friend can taste actually how your pizza is very good. So it's really unsolved, challenging problem, not yet solved, but not something that cannot be solved. There are, of course, some technological limitations how you could do this. Or, for example, in the perfume industry, you would like to taste different perfumes that you want to buy. You have to smell it, or if it is a really nice perfume or not. And if it is nice, then you buy it. And how to do it remotely. You have a mobile phone or laptop, and you want to sense the smell of the perfume you are buying. So it is an additional modality that is only a question of few more years or maybe decades that will be available on either PCs or mobile phones as an additional modality of these multimedia systems. So the systems that is capable of measuring or sensing this smell or taste, transmitting it to the other side, and reproducing this smell or taste to the user, to the receptor. Okay, signals that we emit. So what are multimedia signals that we emit? The main signals is our visual appearance in the space. So our visual appearance, of course, somebody can take camera and take the image of me, so this is my visual appearance. Then, of course, sounds that I produce, speech or singing or inhaling, exhaling, or sounds caused by going around playing music with some instruments. So all of these are sounds that we can produce. Finally, we have this tactile effect on our environment. We are touching something. In ideal case, I would like to transmit also this information, how strongly I'm touching this pen, if I'm squeezing it right very tightly or not. So this tactile information on our environment is also something that I would like to measure and transmit on the other side. And that is nowadays maybe mostly used in these virtual reality systems that have very sophisticated joysticks at the input. They have some kind of force feedback where you can really vary the force that you grab something, and based on this, really the system recognizes this and creates a virtual simulation of your reaction. So if you squeeze something very strongly, maybe then the virtual glass or bottle will be crushed in your hand or something like that. Then we have also this temperature. Your temperature is also electromagnetic wave. Infrared wave is emitted from you because you are hot. So you have a body temperature of 37 degrees. If I take the infrared camera, I can measure this special infrared signal of you. And nowadays it is also very interesting. Why? Because of this contactless measurement of your body temperature, to see whether you have symptoms of COVID illness or whatever. If you have body temperature about 36.5 or 37 degrees, then ideally I would like to contactless measure your temperature based on infrared response. So you have infrared fingerprint, let's say. I take this image that only passes one part of the spectrum, this infrared part of the spectrum, because this infrared part of the spectrum conveys the information about your body temperature. Okay? And if it is calibrated, I can really measure this body temperature quite precisely without being close to you. Okay, so it is our radiation, heat radiation. Then finally we have this chemical effect on your environment, and that is basically the smell that we pass around us. So if we are, well, if we're using some nice perfume, then this smell is something nice. But if we have exercised quite a lot in gym, then probably this smell is not very nice for your environment. Okay, so these are the signals that we as a human are producing. And the basic idea of multimedia system, of multimedia technologies, is manipulation of this media, either for recording, for reproduction or presentation, for transmission or distribution, and of course this reproduction or presentation, again with transmission, requires efficient storage. So if this media can be encoded efficiently, represented with at least as possible number of bits, then that is useful because we are saving bitrate. Finally, the representation must be such that enables analysis and searching of something. So if I want to find all the images that contain a German Shepherd or whatever other dog type, then I must be able to extract this information from still images. So I have some artificial intelligence system, some neural network, and it processes this information for actual images and take different content and make indexes for each of the images. Okay, this image says red car, young woman with blonde hair, it has that and that type of dog or horse or whatever. So based on this analysis, you have several additional meta information added to the actual images, and this meta information can then be used to search large database. So this pre-processing, this tagging, is done in advance. So once the image is taken from the database, it is analyzed, all different parts of the image is automatically tagged, the content of the image, and finally, all of this is written as an additional meta information together with this image to facilitate searching. Later on, if you want to find all the images containing blonde woman, you will just search for that index, for that tag. So just sort out all the images that has tag blonde image set to 1. Okay, so that is regarding the analysis and searching of this media information. One of the most common applications of multimedia is, of course, connecting people, informing people, presentations, learning, but also amusement. So different kind of movies, games, and so on. Okay, going on. We already introduced that these signals are carried by different carriers. For example, the electromagnetic waves are those that carry this visual information. And these electromagnetic waves can be within our visual response of our visual system, and that is this part of the spectrum that we can recognize as red, blue, or green color. But that is only one small part of the whole spectrum that we are capable with our eyes to see as a visual image. And some other animals are capable of seeing a larger bandwidth of this spectrum. Some are able to see infrared part of the spectrum as well. Humans are not able to see the infrared part of the spectrum. Sound waves or sounds that we are hearing, they are actually described, or they are conveyed by the variation of the sound pressure level. So what happens is when I'm talking, I'm creating like perturbations in pressure level. So above us, we have this atmosphere that is 10 kilometers above the surface of the Earth, and this pressure due to this atmosphere is one atmosphere, okay? And the variation of sound pressure level caused by me speaking to you is maybe 100 times or 1 million times smaller than this constant atmospheric pressure. So this 1 atmosphere is like a DC level. And when I speak to you, I create some perturbation of this constant pressure level. And this perturbation is 1 to 100,000 or 1 to 1 million compared to this high pressure level of constant atmospheric pressure. And our ear is still capable of measuring this very slight variation of pressure. So instead of having 1 atmosphere, I have 1 atmosphere plus 1/100th part of 1 atmosphere due to this variation. I'm still able to hear this very small variation of sound pressure level. Okay? And that is for sound waves. For mechanical signals, these are measurable to some motions, to some accelerations or linear motion of objects. Finally, these chemical signals are measured as a concentration of some chemical compounds, some chemical molecules. And based on the concentration, based on the ratio of these molecules, we are differentiating different smells or different tastes, one from the other. Okay. Sensors are those that convert this physical signal to a measurable form that we are able to convert to digital signal. So first of all, for example, if we are talking about electromagnetic waves that our eyes are measuring, how to do it in a multimedia system. I must have an electronic component that is able to do it the same thing, to convert the electromagnetic wave in the visual band into some electrical signal. And how it is done? It is done inside this CMOS or CCD sensor. So this CMOS sensor or CCD sensor that is part of each of these cameras that you have in mobile phone or on your laptop, this sensor really converts the photons to electrons. So what it does, when photons fall on this photodiode, they will the free electrons will accumulate in this pixel well. And these free electrons, number of these free electrons that are generated depend on the number of photons that fell on this active pixel area. And the final quantity of the number of these electrons is actually measured as a voltage on the capacitor, because each of these pixel cells behaves like a small capacitor, and based on the number of electrons, the voltage is larger or smaller, because this number of electrons is nothing else by the electrical charge. So I have the electrostatic charge, I have the capacitance, and based on this basic equation between the charge and the capacitance, I have the voltage on this capacitor. If I measure the voltage on the capacitor, I get indirectly the information how many photons have fell on this pixel in some unit time. This unit time is this exposure time. It is typically a few hundredths of a second, maybe 1/100th of a second, or maybe 25 hundredths of a second, something like that. It depends on how bright is this object. If the object is very bright, I can have this exposure time very short, because there are many photons falling on the sensor. But if the source is very dim, I have to extend this exposure time to have sufficient number of photons falling on the sensor, sufficient number of electrons that are combined, and such that the voltage at the end is measurable. I can take this voltage from the cell, pass it through the AD converter, and have the final readout value that is proportional to the light coming on the sensor. So that is for the electromagnetic conversion of the electromagnetic wave into electrical signal. And then how you can differentiate between different colors, because all of these sensors are more or less monochromatic, so they have the response irrespectively of the frequency of the photon. So it doesn't matter what the frequency of the photon is, it has almost the same response, this photodiode. And to have this discrimination between different colors, they have typically passive filters. So they have a filter that passes only certain band of frequencies, let's say band corresponding to red color. Only certain band of frequencies is passed to the cell. And then, in this case, this cell would measure only the red part of the spectrum, only the red color. And next to this pixel is another pixel that has green filter above it. Below is another pixel, it has blue filter above it. And these RGB filters, they are organized typically in some regular matrix form. They typically have 2 green filters, 1 red and 1 blue. And it is repeated in the periodic pattern along the sensor. And that is the difference if you buy a camera that has 20 megapixels. It has 20 megapixels altogether, all 3 colors. Actually, it has only 5 megapixels of blue, 5 megapixels of red, and 10 megapixels of green. So it is like a commercial trick. You say, okay, I buy a camera with 20 megapixels. Okay, of course. It is only 5 megapixels actually. Okay, so it is a conversion of electromagnetic waves to electrical signal. For the sound pressure waves, microphones are used. And microphones convert this mechanical vibration into electrical signal. There are different ways how these microphones can be constructed. It can be simply a coil that moves in some fixed magnetic field. And based on motion of this coil, I have the electromagnetic force inducted in the coil. And this electromagnetic force, this voltage, this electromagnetic force is then measured as a voltage on this coil. And this voltage is proportional to the motion of this coil in the fixed magnetic field. And this motion is caused by mechanical vibrations. I have a membrane. This membrane is moved left-right due to this varying sound pressure level. And this membrane moves the whole coil left-right, left-right. And I have this electromagnetic induction on the coil that is directly proportional to this motion of the coil. And that is a dynamical microphone. It's called dynamical microphone that uses this principle of electromagnetic induction. It can be also a capacitor. So if I have a capacitor with 2 plates, and if one plate vibrates, I have varying capacitance. And if there is a charge, if there is a constant charge on this capacitor, if the plates are displaced by varying distance, I get variation of capacitance. And this variation of capacitance is then converted to the variation of voltage, because the charge is constant. So if I move the plate and change the capacitance, and that actually changes the voltage over this capacitance. And by measuring this time varying voltage, again I measure the vibration of one plate of the capacitor. And these are the most common microphones used nowadays because they are cheapest to produce. They can be produced in silicon technology the same way as the chips are produced. Okay? They utilize this MEMS technology, micro electromechanical system, that you can actually create a mechanical system using the same technology that is used to manufacture chips, silicon chips. So you can etch on this silicon level wafer some mechanical elements that are movable. You have a movable plate. You have like a spring that defines the constant of elasticity of this plate. Everything you can be doing on this silicon level with this MEMS technology. And this is how very cheap transducers that convert mechanical vibration into electrical signal can be constructed, produced efficiently using the silicon technology. They are also used to measure the direction of a g-force, so g-force acceleration. So this vector going down can be measured. If I tilt the phone here, I have different projection of this g-force vector into the plane of the sensor. And this sensor is also a MEMS component. So based on this orientation, these plates are differently displaced one from the other. And based on this displacement, it has x-axis, y-axis, and z-axis. It has 3 axes of measurement. And simply by tilting the phone, it changes the projection of the g-force vector into all of these 3 axes. And I get the information about the attitude of your phone, of the chip, only by measuring the projection of this g-force vector into the MEMS sensor, measuring the acceleration in 3 directions. This can also be used for measurement of the dynamic signal, not only for the constant vector of acceleration, but if I shake the phone, it can also measure this acceleration in all 3 directions. So nowadays we have very sophisticated, very cheap sensors that are able to measure mechanical signals of either speed or acceleration. So they are the first derivative of the motion or second derivative of the motion. And based on this first and second derivative, they can use different algorithms to actually finally find the angle or the position. So we have to double integrate the acceleration or one times integrate the speed to get the information about the position or angle. And that is done on your phones because they have 2 different types of sensor. One is accelerometer, the other is this gyro that measures the angular speed. By combining these 2 measurements, you can get the actual position of the device, orientation of the device, but you can also refine the GPS position because you can use this information to track the motion in the space. So if I move around, it can measure the acceleration of motion. So exactly as I go left, right, it can just integrate these vectors of motion to find where around in the space I am walking, to refine the information from the GPS to the accuracy of meters or less than meter. Okay, so these are these mechanical signals. And then finally, these are these chemical signals. These are still a challenging problem, not solved yet at the commercial level, but probably in a few years, they will be also available in some new generation of phones, I would say, as an additional sensor to have. Okay. As we said, so the sensors convert the physical quantity into some electrical form that can be measured, that can be easily measured. And the most oftenly, I convert this physical value into voltage, current, or frequency. Different type of transducer for different physical quantities. Sometimes some physical quantity is converted to the voltage on some sensor. Sometimes it is current that is output information. Sometimes it is frequency of the signal. Depending on the something, whatever, temperature, you have different frequency of the output signal. So these are manifestation of the sensor output. So either the current or voltage or the frequency of the output signal depends on the physical quantity being measured. Okay. I said already about the image sensors. So these 2-dimensional sensors for the image or video. These are the old technologies, charge-coupled devices. And nowadays, practically all of these cameras are CMOS cameras, different way that the sensor is implemented. Sensor can work in the visual range, RGB, but can also work in infrared spectrum. And for the sound, I have different electroacoustic converters. I said already dynamical microphone, condenser, or capacitive microphone. Okay. And in the sense of virtual reality, I also have different sensors of motion or attitude. So orientation of your joystick orientation of your mobile phone. So this orientation, the attitude in space, can be also measured using these MEMS sensors. Accelerometers or these gyros. Gyros convert the first derivative of angle into output measurement. And finally, we have this electronic glove. If you want to transmit information about motion of each individual finger or part of your finger, then you have this electronic glove. You can put it on your hand, and simply moving your hand around, it exactly recognizes what you are doing with your fingers. Okay. The main applications or the main tasks for reproduction are what? I would like to reproduce multimedia content. Exactly here is this multimodality that is exceptionally important, because during this reproduction, all of this media must be represented in a synchronous way, interconnected, interactive way. So if I have audio, I have some images, still images, photographs, if I have some video clips, so all of this content must be somehow integrated, connected, and presented to the user. What is this interactivity? Interactivity means that during the reproduction, the user can be able to decide what he wants to skip, where he wants to go. He wants to navigate the content. So the same way as you navigate the HTML web page, going back, following the links, blah, 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 the same way you want to navigate the multimedia content. Why? Because instead of reproducing linear content, like an old movie, you go to movie theater, you sit down and you wait now for 2 hours, look the movie. It is linear content. You cannot go back, skip few commercials or whatever. But with this interactive content, you are able to skip any part. So to jump in any time point in the media content that you want to follow. Okay, that is some slide that shows that this is interconnected. So sound, graphics, text, video, all of this is connected in these hypermedia links. Okay, finally, what we have learned, what are the multimedia signals in multimedia systems and technology, what is the perception for these multimedia signals, and what are the receptors, for human receptors for perceiving these multimedia signals. Then finally, if the human is the source of multimedia signal, what are the signals that we are emitting? So how we can finally measure these signals and transmit them to the other side. What is multimedia signal? So how this signal is captured and reproduced at the other end. The idea of interactivity and hypermedia content. Now we have 5 or 10 more minutes. So just as an introduction to the second part of this first presentation is short about the evolution of multimedia. So before we had computers, presentation of different media content were related to different dedicated devices for reproduction. For example, somebody maybe can recognize what is this. So for very old turntable, so phonograph, playing music LPs, for example. And then in the newer version, this is this phonograph. And this is a 8-track recorder, so it is based on magnetic tape, and it was capable of recording not only single audio stream, but several streams on the same magnetic tape. This here is a cinematic projector, dia projector, diapositive projector, and another cinematic projector, maybe more modern than this one. And this here is maybe also recognizable to some of you. So this is graphoscope. So you would place a transparency here on this glass lens. And this image of this transparency is then reflected through this mirror on the wall. So it was like a predecessor of PowerPoint. Everything had to be drawn on this transparency by hand, by some fine pens, and then it was reproduced with this graphoscope. But of course, all of this is history, because with the advent of computers, they were the main driver of these multimedia technologies, because nowadays, a computer that is connected to the internet is more or less universal integrated system for reproduction of any multimedia content, but not only reproduction, more or less they are also capable of recording any multimedia content, and that is especially true for mobile phones, because they are really, they integrate all different modalities of signals, so video, audio, whatever you would like, and with connectivity to internet, you are able to stream this content directly to the web. You don't have to store it here locally. Directly emit to cloud servers, and the content is stored and immediately redistributed to any user around the world. So that is really huge transformation driven by the capabilities of such computers that are integrated in your small mobile phones. Nowadays, computers are really capable and able to do all of these tasks related to multimedia reproduction, but also recording. With the advent or with the evolution of this technology, the quality standard of reproduction are better and better. So these standards are of higher and higher quality, and requirements of multimedia systems are even more stringent than before, because nowadays these multimedia systems can really reproduce high quality video content, high quality sound content, but people are never satisfied, so they always want more. In that way, it will always be enough job for you as a future multimedia engineers to develop new solutions, new technologies that will be integrated in some future systems. So this is like a multimedia computer, okay, and like a universal system for reproduction. And as I said, nowadays, possibility to reproduce multimedia content, but also record multimedia content anywhere and any time, any place. So, of course, nowadays it is already realized. This task is more or less realized using mobile phones. Mobile platforms for reproduction, so different media players, all of this is now integrated into smartphone. So media players, before it was dedicated device. So it was iPod player, it only played audio or video, iPod video for playing video files. These were not connected to the internet. So they had only storage, fixed storage on the device. What you put on them, you could play, but that's it. You could not connect to the internet. Then, of course, mobile phones that have capabilities of reproduction, and they have the advantage because they are connected to the internet. These handheld computers, or palm computers, before it was again a dedicated device. It was not an integral part of a smartphone. This organizer, email client, or whatever, it was part of this device, this personal organizer. It was not implemented on your mobile phone. But with the advancement of capabilities of mobile phones, all of these functionalities are finally integrated into a single device. Okay? You can see in 2008 how it looked like. So the concept that you would have a camera on your iPad or whatever, something like that. It was maybe 1 inch thick. Then some mobile phone that had a camera in this corner capable of reproducing video. Or again, some Nokia N95 3G phone also had some kind of multimedia capabilities. But that was state of the art in 2008. So you can see how much it's changed in only 13 years. It is really incredible. So the development of multimedia, we have nowadays a huge number of different systems or devices that can reproduce multimedia content, but they have large differences in processing capabilities. So some of these platforms have sufficient computing power, some not. Some are maybe less advanced or older version of CPUs. They have differences in the resolution of the screen, in the size of the screen and quality. They also have the differences in power consumption and battery power consumption. That is especially critical if you want to stream whatever, some video file for several hours or whatever. Then it depends on how well it is implemented on your phone and what is the capacity of the battery. So the differences are between different phones in the performance for this video streaming or for video playback. There are differences in the capacity of the memory or for storage. But nowadays, more or less, the content comes from the internet. So the storage on the phone is not critical as it was before. Before you must have several gigabytes or whatever of flash memory just to store the content. Nowadays, more or less, you take the content directly from the web. And then finally, what is the capability of your connectivity to internet? Because some early phones had only small rates of connectivity to base station for this second generation, third generation. Nowadays, these rates are much higher, and especially if you're on local network, if you're on Wi-Fi, normally all of these phones can connect to Wi-Fi, and once you're on Wi-Fi, these rates can be also hundreds of megabits. And finally, there are differences in operating systems, but more or less it has converged to only 2 operating systems, so it is either Android or iPhone, iOS. But before, they had even larger number of operating systems on the market. And due to these different multimedia platforms, we have specific requirements on the organization of multimedia content. And there is a requirement for scalability or for scalable format in a way that all devices should be able to reproduce the same content, but in accordance with the capabilities of each individual platform. And for example, you know that on YouTube you can select the bit rate that you use for streaming and for reproduction of video content. And this bit rate must be adjusted to the actual connectivity rate of your channel that you are connected with. So if you select, I don't know, 1000 whatever, it cannot pass through the channel. You have to select the lower resolution, lower rate, in able to have the real-time reproduction. And how to organize the content in a way that you have the users that are connected with the high-speed networks. They want to have the high quality, full quality of the video content. At the same time, you have to support also users that have low connectivity rate for the network, and they must be able to view the same content, but with a lower bit rate. So this is how to organize this content that should be scalable in bit rate and quality. Okay, that is the last slide. We'll stop here, slide 56, and we will continue then in 1 week time. So does this 4 o'clock is okay for you, 4 to 7? Yeah. Okay, so then we'll see in 1 week time. I will share the link of this recording to you, and then you will be able to offline view this recording if you would like to prepare for exam or whatever. Okay, so that's it for today. If you have any questions, ask. You can also ask with any technology of communication from email, and we will initialize this Teams group for the multimedia course, and you will be all added to this group, and later on you will be able to follow all of this conversation and material exchange in this Teams group. Okay, then see you in 1 week time. Bye-bye.